Hey guys, how's it going? Good morning, good afternoon, good evening, whatever time you're watching this. This is going to be a way for me to be able to convey a lesson to you in the event that I'm not present. You never know with a year like this if this is going to happen because of COVID or just a general absence, but the show must go on, as they say, whether I am there or not. So this is going to be a means for me to be able to convey lessons and information to you in a different way. So this is for chemistry honors. What we're going to be going over today is, radiometric dating, and we're going to be doing half-lives. Okay, so let's go ahead and get right into it. In case you didn't know, the Earth is approximately 4.5 billion years old. Now, you might be like, well, how do you know this? You weren't there. No one was there. How can we possibly comprehend the fact that the Earth is that old? And that's a very fair question. How would anybody know that? Well, there's been a lot of different practices that have been utilized to try to determine the age of certain things on Earth, whether it be a Tyrannosaurus Rex fossil, King Tut's tomb, the ancient pyramids in Egypt, or not South America, Central America. Yeah, I guess South America. We're always trying to find out just how old things are, and what better way or what better object to determine the age of than the Earth. And then we figure out the age of the solar system, and then we figure out the age of the universe. But let's just take one thing at a time. So as you all know, there are 92 naturally occurring elements that you find on the periodic table. And the number 92 is uranium. Well, when it comes to calculating the age of any sort of remnant in the history of time, we have to think about this concept of radiometric dating. And what radiometric dating does is it calculates the decay rate of radioactive isotopes. Well, some radioactive isotopes decay at different rates. So one thing that we do know, and one thing that we have found out, is that uranium-92 has a half-life of 4.5 billion years. So to give you an idea of what I mean by this, let's say that I have a form of uranium. It could be uranium-238, but we're actually going to use the really radioactive form, uranium-235. And uranium-235 has a half-life of about 4.44, something like 496, something like that. We're just going to say 4.5 billion years. So imagine that at 0 years, I had 100 atoms of uranium-235. Okay? After 4.5 billion years, I will now have half of this. I will have 50 atoms. And then after another 4.5 billion years, which is going to be 9 billion years later, I would have 25. These are called half-lives. And I'm going to get all into half-lives a little bit later. But this process of radiometric dating is all about using radioactive isotopes to determine the age of various artifacts that are all over the Earth, whether they be man-made artifacts, they be naturally occurring like rocks or mountains, or the fossilized remains of prehistoric creatures. They're all going to be or capable of determining the age of by calculating the half-life. The half-life is going to be simply how much time it takes for half of that mass to decay away. All right. So radiometric dating is simply the process of calculating how long it takes half of a radioisotope to decay. And the key here, folks, is how long. We can determine the age of many things using different radioactive isotopes. So one popular radioactive isotope is going to be carbon-14. Now, before I get it all into carbon-14, let's talk about carbon-12. So I am going to go ahead and say that carbon-14 is radioactive. It's unstable. But let's talk about the good type of carbon, or maybe not, that's a little judgy. The most predominant form of carbon is carbon-12. We are made up of carbon-12. Carbon-12 has 6 protons and 6 neutrons. It is stable. But in the upper levels of the atmosphere, nitrogen-14 can be converted into carbon-14. And there is a little bit of carbon-14 in every living thing. You, me, your dog, your goldfish, your neighbor, the tree outside, the insect crawling around, all of it. There's a little bit of carbon-14 that is present in every living thing on Earth. Well, carbon-14 has a decay rate of approximately 5,730 years. What the heck does that mean? That means, again, if I had 0 years and I had 100 atoms of carbon-14, after 5,730 years, that would be cut in half, approximately. And then at 11,460 years, we would be down to 25 atoms. And then at 17,190 years, you'd be down to about 12.5. And so on and so on and so on. So with every half-life, you are cutting it in half. So here's one half-life, here's a second half-life, here's a third half-life. So after 3 half-lives of carbon-14, which is 17,190 years, you're going to have less of that atom or of that radioisotope, but we can calculate how long it took. How long did it take for 100 atoms to get down to 12.5 atoms? The answer to that would be it took 17,190 years, or we could just say 3 half-lives. And just to put the cherry on top, 4 half-lives would be 22,920 years. That would be about 6.25 atoms. And that's the 4th half-life, okay? So very simply, radiometric dating is just using radioactive isotopes called radioisotopes to determine the age of various things on Earth. We know that the solar system and at least the universe are older than the Earth because there have been asteroids and meteorites that have hit the Earth. We have calculated their age, and they are older than the Earth. There's been things that have hit the Earth that have been calculated to be 4.6 billion years old, 4.8 billion years old. So we kind of get an idea of how old the universe is, how old the Earth is, the moon, and ultimately the entire universe, which I'll go and give it away. The entire universe is about 13 billion years old, based on the evidence that we have at hand right now at this time in human history. Okay? So, give me one moment here. We can determine the age of the Giza Pyramid in Egypt. The Giza Pyramid was approximately constructed in 2054 BC, which puts it around just a little bit around 4,000 years ago. Sue the Tyrannosaurus Rex. If you ever go to the museum in Chicago, there's a very famous completed skeleton of a Tyrannosaurus Rex. And through radiometric dating, That has been calculated to be about 66 million years old. And then we have the big mama. We have Mount Everest, the tallest mountain on Earth. It's in the Himalayan mountain range, which is around India and Tibet. It is where the country of India used to be an island, and it just plowed into Asia due to plate tectonics and continental drift. It is about 60 million years old. And this is due to the radioactive isotopes that are found within these structures or within these fossilized remains. And the half-life of them is calculated, and we can determine how much is left and how much has actually decayed over time. So there is a little bit of a math equation here, and that is how to actually calculate the remaining amount of a half-life, or the remaining amount of a radioactive isotope. So in order to calculate this, we have an equation. Okay, here we go. All right, we have a lot of variables here. This is the formula that we use to calculate half-lives. And you will be given all the numbers, you just have to plug them into the right place. So N is the remaining amount. N naught, and you might say N zero. Well, in science, we say zero is naught. This is the initial amount. And the superscript N, or the exponent, is the number of half-lives that have passed. And I would need to be very clear with you on all this. It does not say the number of years that have passed. It says the number of half-lives that have passed. So if I go up here, if I asked you, how many half-lives passed, guys? And you say, 22,920 years, Mr. Thorson. That is not correct. You have to listen to the question carefully. I didn't ask how many years passed. I said how many half-lives passed. 4. 4 half-lives passed. And you can expand on that. You can say 4 half-lives, which equals 22,920 years for carbon-14. But this represents how many half-lives have passed, okay? So let's do a quick math equation. This is all from your PowerPoint. I'll break it down. You need to have a calculator out, so I'm going to write this out. Krypton 85. So if I were to, actually write that, Krypton 85 is used in indicator lights of appliances. The half-life of Krypton 85 is 11 years. So what that means is it takes 11 years for however much you have of Krypton 85 to decay into half of that amount. How much of a 2.000 milligram sample remains after 33 years? Okay, so you need to write your known and unknown values, and this is going to be a great exercise for us because as this year goes on, I'm going to be asking you guys every time, very disciplined, to write down your known and unknown values, what you are being asked to find and what are you provided. It is going to be very, very crucial that you organize all your information. So what we know is that our initial amount is going to be 2.000 milligrams. the elapsed time that went by is going to be 33 years. And it tells you that a half-life is 11 years. So the first thing you need to do is you need to try to calculate how many half-lives are there in 33 years. So the first thing, guys, and actually before I go through this, the unknown is how much of 2.000 milligrams of krypton 85 remains after 33 years. Okay? So, you need to try to figure out how many half-lives are there in 33 years. 33 years equals blank half-lives. That would be 33 years divided by the length of one half-life, 11 years, that's going to equal 3. 3 half-lives. So 33 years is 3 half-lives. 33 years, which is the amount given, divided by the length of one half-life, which is 11 years, that's going to be 3 half-lives. So now all you have to do is simply plug in your values. Remember that n naught times 1/2 to the nth power is our equation. N naught is going to be your initial amount. So that's going to be 2.000 milligrams times 1/2. How many half-lives passed? 3. So if you get out a calculator, you have to do 2 times 0.5 times the third power. You should get about 0.2500 milligrams. That is the amount remaining. Okay? That is how you calculate half-lives. I think you have a couple of half-life problems in your homework. One last thing I want to address before we wrap this one up is carbon dating. Like I said, you all have carbon in your body, and hypothetically speaking, this is, let's say that I died. I'm not going to use any of you because I don't want you all to get upset. Let's say that I died today and you guys buried me under Plan High School. Well, long into the future, long into the future, they find my bones just lying there in the footprint of Plant High. Well, as soon as I died, and as soon as any organism on Earth dies, carbon-14 begins to decay. Now, it's a pretty much uniform number as to how much of the carbon that is inside of our bodies making us up of what we are and who we are. It's pretty much determined and understood of what percent of all the carbon in our body is carbon-14. So we know just by walking around what percent of all the carbon in our body is carbon-14. So what we can do is we can compare how much carbon-14 is left versus how much carbon-14 we should have started with. So it basically works out like this. When you have, the x-axis is going to be the fractions, or the fraction of elements present. And the y-axis is going to be half-lives years. So we have 1 half-life, 5,730, 2 half-lives, 11,460, 3 half-lives, 17,190, 4 half-lives, 22,920. So at one full half-life year, or excuse me, when you have one whole, you're at 0 half-lives. So we're going to start here. Okay? When you get down to half of your original amount remaining, 1 half-life has passed. When you get down to 1/4 of your original amount remaining, 2 half-lives have passed. When you get down to 1/8 of your original amount remaining, 3 half-lives passed. And I could just keep going. 1/16, 4 half-lives remaining. So as we go forward in time, the amount of carbon-14 that remains in our remains is much, 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 much smaller. So just hypothetically speaking, let's say that in my body, when I was living, I should have had, again, hypothetically, I should have 100 atoms of carbon-14. Okay? That would be at 0 years. So I died then. At 5,730 years, I should have 50. That's 1 half-life. At 11,460, that is 25 atoms. That's 2 half-lives. At 17,190 years, that should be 12.5 atoms. That's 3 half-lives. And at 22,920 years, that's about 6.25. So let's say that you find my remains at Plant High School approximately 17,000 years from now. So, SpongeBob, 17,000 years later, you find my body. I'm nothing but bones, femurs, ribs, spine, skull. That's it. That's all that's left. And through carbon dating, scientists are able to determine that I have 1/8 of the amount of carbon-14 that I should have. So, this is 1/2, this is 1/4, this is 1/8, this is 1/16. So scientists are able to determine that this skeleton, this human skeleton, has 1/8 the amount of carbon-14 it should have. Well, they calculate 1/8. So if they say he has 12.5 atoms, when he should have 100. So carbon-14 has a half-life of about 5,700 years. So we're able to determine it went from 100 to 50 in 1 half-life, 50 to 25 in 2 half-lives, and 25 to 12.5 in 3 half-lives. I've been lying there for about 17,000 years. Now, for things on this earth that are a lot older, dinosaurs, rocks, mountains, we use isotopes that have a much longer half-life than carbon-14 because in the grand scheme of the history of Earth, 17,000 years, 22,000 years is really not that long. So we use elements that have a longer half-life. And the element that we know of so far that has the longest half-life is uranium, which is about 4.5 billion years. So that means that all the uranium that is on Earth now is half of what there used to be. It has spent 1 half-life decaying. So in order for the half of the uranium to be here, it had to have started as one whole. And that means that the uranium was here on Earth 4.5 billion years ago, which lets us know that this Earth is at least 4.5 billion years. If new information comes up, we would have to adjust, but this is pretty sound science. And so it is agreed upon in the scientific community that the Earth is this age, and that is due to radiometric dating, which is calculated by determining the number of half-lives. Okay? All right, that concludes this lesson.